Doing the political aspects of the landscape issues in the Solomon.
Tell whether what he's saying.
Well, I guess it's like I was gonna ask you today. It's like, I mean, you can, for example, I'm focusing on the three major like countries that finish in the Solomon, which is China, Taiwan, and Japan. And it's like there's the highest catch. But then there was like something that's political thing. Taiwan got rejected 2 years ago for illegal fishing, and it doesn't actually show. On the thing, so
That's hilarious.
the thing is, I don't know how you can vote. Like, do you just put a graph or expand? Yeah.
So we're late. It's Vanya's fault.
It used to be.
No, it's not.
There's like some fleet of that sort of stay for a couple of years before going back to land. And some of them have like fish and just this kind of, I don't know what it's called. I think it's called trench shipping.
Okay, apologies for being late. All my fault. I was too busy with emailing. Always the usual excuse, right? Okay, so today we'll be covering some of the basics around stock assessment. Heads up, I'm not a stock assessment biologist. I'm not a mathematician. I used to do quantitative ecology. I used to teach basic statistics a long time ago when we still used slide rules and stuff like that. But I'm not a stock assessment scientist, so I'm keeping this simple. I'm trying to cover the principles rather than the details. But if you're interested in it, there is a huge field of literature and opportunities in stock assessment. So, back to basic principles, right? So we exploit, and remember exploitation, fish in their natural environments. And if there wants to be any form of sustainability, we first have to define that. So how do you define sustainable or sustainability? Any ideas? What's the most basic principle behind sustainable or sustainability?
That it's renewable.
What do you mean by renewable?
That future generations can use that source resource as well.
Okay. All right. But if I fish something down and I just fish it down slowly, you can still, future generations can still catch some. Is that sustainable?
No.
Okay, so what's missing from your
So
definition?
it means that.
Stop. I want others to speak too. Right? So, yeah.
Maybe like a viable population.
Viable population, what does that mean?
I don't think sustainable, but
Circularity, right? It's so easy to fall in this trap. Well, something's sustainable when you can sustain it, right? But that's a circularity of argument. For definition, it doesn't work.
We can keep catching the same amount.
Right? I think yesterday you would have earned yourself 10 bonus points for something you said. You would get another 10 bonus points if I could give them, right? You can keep doing the same thing over and over. So sustainable means to do something forever, right? I think I have that here. What is the meaning? Whoop. Okay. So it means that you can maintain or do something at that level forever. Okay. So that automatically means you might have heard about things such as sustainable development, even sustainable mining, even oil and gas sometimes talk about sustainable businesses and so on. That's a lie. None of those things you can do forever because we're exploring those resources at a level that far exceeds what the earth produces. The way we dig up oils and iron ore, right, is orders of probably thousands of orders of magnitude higher than geological processes produce iron ore. Therefore, it's not sustainable by its very definition. None of it. Okay? And in business, the term sustainable means in terms of their business cycles. They don't care 5 or 10 years down the track. They talk if something works really well for the next 5 or 10 years, that's sustainable. But it's not sustainability per se because you can't do this forever. Okay? So, therefore, if we accept that definition, what does it mean sustainable in fisheries? Next question for you.
If you can keep catching the same amount forever and ever each year.
Okay, and that means if you can catch from a population, what does that mean for that population?
That it's replenishing at the same rate you're catching.
Okay, so that whatever is caught is being replenished. Okay, yeah. But that would mean, that's correct, but that would mean that we could actually have a sustainable fisheries for blue whales. As long as you only catch one blue whale every 5 or 10 years. I don't know if it's 5 or 10 years or whatever, but you get my drift, right? Blue whales are very slow growing. They produce very few young. It takes them a long time. So probably we could have a sustainable whale fishery as long as we only catch 1 or 2. Is that true? Theoretically?
You have to still be able to meet demands.
Yeah, but with sustainability, I don't care about the demand side of things, right? Yes, it drives a lot of things that's going on in fisheries, but for our discussion now, it's not. So yeah, you could theoretically do that. Just like we could have a sustainable iron ore mining industry, extracting what, maybe 1 ton globally per year or whatever. Someone have to calculate it, right? But that doesn't really work for us, right? Unless we get rid of most humans. Okay, so the issue is, right, that we have to maintain the stock that we fish at a certain biomass level that allows us to take the catch that either we want, okay, or that allows us to take this level forever. So we need to consume, in terms of catching, only as much as the stock produces, right? But there's a catch, and we'll discuss that catch. So in order to do this, that we can figure out how much can we take in terms of catch, we need to know the biomass status, right? And so we need two things. We need to know the condition, which is the biomass status, right? And we need to know the effects of whatever level of fishing we have, i.e. how much will this produce in terms of catch, because those two are in interplay. And that's where we come to the basic steps in stock assessment, because stock assessment does exactly that. It determines what the current biomass level is in light of what was taken, and then projects forward of what the biomass would be next year, and therefore what catch we can take next year if we want to maintain it at that biomass level. Okay, and so this is the theoretical concept behind stock assessment. First, you define your unit stock. What the hell am I even looking at? Okay, you need to know the catch data. You ideally should also have the effort data for the whole fishery that exploits that stock, and you take those two, and that gives you an initial catch per unit effort time series, which is the first indicator of pattern over time. However, that sometimes is even being skipped, or it's not being trusted or relied upon. There's lots of reasons, and that's why many fishery scientists collect a lot of biological characteristics of the stock. I already alluded to that earlier. Things on growth, mortality, stock size, and recruitment. And then they use all of that in fancy mathematical models that I just scratch my head and that I don't understand because I'm not a mathematician, to derive estimates of what they can take next year, which they very often call the yield, right, under various conditions of fishing pressure. So what would happen if we reduce fishing pressure? What would happen to the biomass and the catch? If we increase it, or if we keep it at the same level? And there are various methods. And you come across terms like surplus production, surplus yield, or biomass dynamics models. They are more or less similar things. I will talk about surplus production. There's also what's called yield per recruit models, and then the gold standard age structure models, which means for that you need age of the species. And that's, as I said, that's the gold standard. And fisheries departments around the world all try to do age structured because it's the gold standard, it's the best model, it's the most reliable, it's the most accurate models. There's a whole suite of them. But it requires you to know the age structure of your species. That means you got to do otolith work to age the fish that you catch. It's very expensive. When we go up to the lab in a couple of weeks' time, after mid-semester break, you will be taken through the aging process. You will learn, you will see how they do it. It is very labor intensive and can be very expensive. But it gives you the best data you can use, right? And the stock assessment scientists who will talk to you about this, they will point out that even here in WA, not all species have age structure models because that's expensive and time consuming, okay? And so whatever method you can use, whatever data you have, you then provide advice to managers on this is what the stock has been doing, this is the trend of the stock, this is what we recommend as catch next year if you want to either maintain this biomass or stop a decline, or hey, biomass has been increasing, we could actually take a little bit more if that's what you want. Okay. Now, whether the managers will act on it, and I can't spell, managers, not managers, whether the manager will actually act on it or not, that's a different question altogether. Completely different question, because very often they don't. So we've already talked about stock definition, right? Self-contained breeding population, but that's very difficult to determine because it is just one of those uncertainties, because you don't know where this fish is going to go to spawn and how it's related to its neighbor. Okay. Plus, most fish have a dispersive planktonic stage, which makes it even more complicated. Okay. Right? And spawning grounds and distribution is very important components. Right? Now, genetics, of course, could help determine that, but again, that becomes very expensive. And how much genetic data can you sample from a population that might have millions and millions and millions of fish that intermingle? Okay? And while I did list it first, you need to know what you're talking about in terms of stock. It very often is one of the last things people consider, or it's being done somewhat arbitrary. Right? And this arbitrariness very often is based on history and on experience rather than hard facts. Okay? Because very often we don't really know how these species populations and subpopulations structure themselves. So here's an example from Europe. Okay? So these are the various different populations or spawning seasons for herring. Right? And so they consider this Norwegian spring spawners to be a separate stock from the Icelandic summer spawners. Now obviously if they spawn in spring and the other one in summer, you would kind of assume they're separate populations. But is there gene flow or not, and therefore is it a separate population? We may never really know, but one thing you really notice is some of the boundaries are very arbitrary, right? No fish recognizes a line like this, okay? So therefore convenience, they're sometimes for political reasons, Norway versus Iceland. Sometimes there's simply a convenience based on experience, where fisheries and fisher scientists know that most of the herring down here do behave as a population separately to the one here. So there might be genetic flow between them, but it might not be sufficient to actually really make a difference in terms of the purpose that we have here. Look at the Baltic Sea, right? So an overlap area and then 1, 2, 3, 4. Right? Is this real? Evidence seems to suggest that they more or less can be treated separately. Okay? So there's an arbitrariness to this. Here's another picture for herring, making it even more complicated. Right? So we have autumn spawning herring and spring spawning herring. And look at the distribution of all this. Okay, I have no idea why these are here, but there might be a fjord or something, so there might actually be some spawning way up deep inland in the fjord. Okay. So there is an uncertainty around it, but fishery scientists, particularly the local experts, they do the best they can, and they really very often understand their species. But sometimes they all say, wow, I didn't expect that. For the last 20 years, we treated them as different stock, and now we realize they're not. Okay? So it's an evolving field, and there's constant consideration about this concept of what defines a stock. Okay? So, having jumped over that first hurdle of uncertainty, we have to get the data, right? So, we need catch and effort data at the minimum. And catch data, of course, you got to ask, where does it come from? Who's collecting it? How reliable is it? How complete is it? So there are logbooks that in some fisheries fishermen have to fill in, compulsory. Sometimes it's voluntary. Both of those have different certainties around them. Okay. There's also very often in landing ports, there are site enumerators, government officials who actually measure or weigh the catch coming off or count the number of boxes of frozen fish being unloaded. Okay. There are also sometimes spot inspections. Very often, if you have close cooperation between the fishing industry and management, then fishers' co-ops very often take on part of that role, and they very often try to self-regulate, right? And as long as they do a good job, there's trustworthy data there. Then, of course, we got what I would consider a little bit the gold standard in terms of catch data and effort data. That's onboard observers. So that's an independent observer that's on board the fishing vessel and records everything that comes on, independent of the skipper having to also keep a logbook. This can be either in person or even electronic or video system monitoring. It all has its advantages and disadvantages. Okay, there's some real concerns about some of the onboard observers if it's in person. People have disappeared, they've been killed, they've been thrown overboard. So it can be very risky business. And when it comes to non-commercial fisheries, the whole thing is even harder. Like if you talk about recreational fishing. Very often you have to go to survey methods. Creel surveys, questionnaires, either in person, by mail, or by phone, or online. Right? Or you do boat ramp surveys. All of that has a massive amount of uncertainty around it, depending on how you design it, how much data coverage you have, and so on. So there's lots of sources of this data, all of them with their caveats. Okay, and that tells you something about the reliability, the accuracy, and the precision of the data that you're getting as a fishery scientist, a stock assessment scientist. Okay. And then we come to fishing effort. And again, you can have similar data sources measuring this than for catch, all right? But there we have a problem. Because usually effort is very, very fisheries specific, because fisheries differ by gear types, right? So we might have the northern prawn trawl fleet. These are bottom trawlers. So you might be measuring that in trawl hours. How many hours per week does a trawler actually have to trawl in the water fishing? Okay, if you have a different gear, a long line gear, trawl hours is meaningless. So you use a different unit. Okay. And very, very common is the number of boats in a fishery, maybe by length class. Okay. For example, the number of large versus small trawlers in a northern prawn trawl fleet. However, that is just the static effort, the nominal effort. Because the number of boats doesn't tell you anything if none of those boats ever leave harbor. Or some might go fishing for one day, others might go fishing for 6 months a year. So you need the effective effort, which takes fishing time into account. Okay. And therefore, your actual effective effort, which is, for example, the number of boats multiplied by the number of hours that they fish, is a key measure, which helps you to work towards what you need to understand, what you need to understand, which is the fishing mortality that this imposes. But then the question arises, if you only work within a fishery, if you only, as a stock assessment guy, interested in the prawn trawl fishery, then fishing hours per trawler size is perfectly fine. But if you work across fisheries, okay, then you get the problem of standardization, because every gear will have a different measure of fishing effort. Okay, trawl hours, long line hooks, and so on. Okay? And so how do you standardize across this? It's very difficult, right? Most fisheries never ever do this, because stock assessments works within a fishery, within a stock. Very few of them, as I told you in the global lecture, most fishery scientists work at the tactical level. They never take the bigger steps, so most of them don't have to do this. How do we standardize across? Okay. And I've already talked about fishing gears, but there will be a separate lecture, I think, next week or the week after, on catch per unit effort, which talks a little bit more about that. Okay, but if you have catch and effort, you can get these CPUE trends. So catch per unit effort. What can that tell you? Anyone happen to know? No, that's fine, because we haven't had that lecture in detail yet. So, but let's summarize it here. So, if the catch in your fishery changes at the same rate as the effort, okay, so either catch goes up and effort goes up, or catch goes down and effort goes down, then that relationship, the catch per unit effort, is a flat line. Does that make sense? If your catch goes up, your effort goes up, the rate of that is a flat line. Okay? So that's a flat line. If the catch increases, while the effort either stays flat or decreases, right, your catch per unit effort actually increases, because you're putting less effort into for more catch, or for the same catch, right? So you get this sort of trend. But if your catch decreases or remains flat while your effort increases, so you're trying to put more and more effort into it, but you're actually not catching more, you're catching the same or you're catching less, right? Then your CPUE declines. Okay? So it's actually a declining trend. And so these trends actually tell you something really, really crucial, as long as the data are representative. And that's a lot of criticism around CPUE. Okay? Because these CPU trends, if they're standardized for a fishery, they can tell you something about the relative abundance of the underlying stock. Because if you increase your fishing effort and you try to fish more and more and more and more, but your catch is actually the same as decreasing, all right, that tells you that the underlying stock, there's less and less and less of them there, because you got to fish harder and harder and harder to get the same or less catch. Okay, that's what is mean by relative abundance. It doesn't give you total biomass, but it gives you a trend over time. Okay, so that's why CPU time series are good first indicator about what's going on in your fishery. Because if they are declining, that's a warning sign. And then you got to look really closely. But that's why I say you got to standardize it and you got to be very careful. If there have been management interventions that work on the effort, then the effort trend that you might get may not be a natural trend, but might be curtailed or limited by fishing actions. And then you got to be very careful interpreting your CPUE. Okay, that's why you need to, if you want to use this specifically, you need to be very careful about it. So here are some examples, right? So this is a research trawl survey of cod in the North Sea. So the unit is numbers caught per hour trawled. And you see, since 1970, there's been a decline. Okay? So on face value, you got to watch out. But has there been a curtailing of the trawl effort through management? Probably has. Okay. Here's another example. But now the units is number of lobster per 100 pots per 24-hour soak. Also been going down. Don't know if there's been management action or not. But how do you relate this unit to this unit if you want to look at the same thing, North Sea, across fisheries? How do you standardize that? These different units. Okay. Okay, so that's about CPU, and we'll talk more about that in the separate lecture. All right. And so most fishery scientists, as I indicated a few times, they start trying to acquire data, biological data underlying the species, because they want to have multiple approaches. And they don't just want to look at catch per unit effort if they can get better data, because they want to get at the biomass, the underlying biomass. Okay? So, growth, and remember there's somatic growth, which is what I'm talking about here. Not talking about the population growth rate. Here I'm talking about somatic growth. Okay? So, and very often there's two types that scientists talk about, because scientists always like to make things complicated. Right? And particular stock assessment scientists like to make it overly complicated, and even more complicated, which is why I don't pursue stock assessments, because I just get, why make things complicated? I like making things simple. Okay. So there are a couple of approaches that scientists take to try to get a handle on growth. Okay. You can, if you can age the fish, you catch a fish, you have its size, and then if you age it, you know how old it is. So you have what's called size at age. So you might know that a 2-year-old fish of a species, of certain species, is somewhere between that and that in length. So that gives you the size at age. Okay? And the other thing, of course, you can do is you can measure it live. So if, for example, you catch a fish, you tag it, and you measure it and let it go, and then a couple of years later you recatch the same fish with the tag, you know which one it is, and it's grown. Okay? So you get size, change in size over time. Okay? And the second has a big advantage. It's cheaper. Okay? All right? And size, so length, is usually preferred over weight when you measure this, because it's easier to measure. Especially on board a boat, when you catch fish and you want to release them again, it's easy to to measure their length. But on board a ship, a scale, if you want to weigh the fish, I mean, it's pretty useless, right? If the boat moves, it's really, really hard to actually get weight for it. That's why many studies look at length. If they don't keep the fish and age it, they look at length. So particularly in developing countries, you actually find a lot of length-based methods are being used. Whereas in developed countries, very often age-based methods are used. Okay. And so here, these guys down here, Ray Hilborn, you've probably heard about him before in my lectures, and Carl Walters, and Steve Martell. He's no longer an academic, he's a consultant now. But those are some of the world leaders in advanced stock assessment. So if you want to really interested in it, they are the hot bodies to read. And this book here is still a classic. So if you got the nerve to read through 570 pages, he really delves into analytical stock assessment. Okay. Now in terms of growth, somatic growth, the most fundamental principle is the fundamental lengthy growth function, VBGF. Okay. And it's the most widely used model, and it applies to basically all aquatic water-breathing organisms. Okay. And it basically measures the growth of how a species with age or size grows, right? And you will see the basic trend. So when they're younger, they grow faster, and then it kind of levels off. So it's an asymptotic growth curve. There's a huge amount of literature around this, and the most recent principle declaration behind this of why this is for all and why it applies to all water-breathing animals is actually called the Gill oxygen limitation theory, GOLT, G-O-L-T, proposed by Daniel Pauly in a book and in lots of papers. It's being challenged constantly by physiologists, and I don't want to spend any time talking about it here, but it's a huge field of future research. And it actually explains why all water-breathing animals do this. That's a mathematical formula for it. Okay, and key parameters of this, and you need to know of this one, you need to have heard about it, and you need to understand that it describes the growth, and it's an asymptotic relationship. Okay, and so you want to know the length at a given age, right? So T is the age, L inf or L infinity, that's the asymptotic length. Okay, it's not the maximum length necessarily. You can have fish that are larger. It's the species average asymptotic length. Okay. You got the growth coefficient, natural algorithm, and T0. So, and T0 is interesting because T0 is actually the length, the age at which a fish, right, would have a length of 0. And you would assume that's H0, right? A fish is 0 millimeters long before it gets born, right? But remember, this is a mathematical model, okay? And T0 is, as far as I know, always negative in VBGFs. Okay, I want to spend a minute on this. Okay, so T0 down there is actually negative when you measure growth. Can anyone think of why that might be? Because it kind of implies that down here something is going on at a very early age or very small sizes that doesn't seem to match that.
Is it considering embryonic development?
Sorry?
Is it considering embryo development?
No, it's not embryonic development. But even if you would have that in there, embryonic development, it's a positive size, not a negative, right? Or age, right? No, it is because at very small sizes, the physiology is different. Because tiny little fish are different. And that's one of the first things that Daniel realized during his PhD in the 1970s of why his Gill oxygen limitation theory is the reason behind this. Okay? And so anyway, at very small sizes, this falls down. But here, at this end of it, it works and it describes the growth. Right? So you just need to know that T0, it's not real, it's a mathematical arbitration of the equation. Okay? So at very small sizes, very young ages, fish grow differently. And very often you actually have an exponential growth, very early ages. So in reality, if you would want to start fish at 0, they actually would do this. And then they go to this. Right? Because the physiology is different with very small fish. Mortality. Okay. So in fish, unlike in mammals, you usually have mortality as an exponential decay. Right? Why do you think that is? Why do you think fish versus mammal behave differently in terms of mortality?
Because they produce lots of young and they will high mortality.
Yes, but why do they produce lots of young? And why don't mammals not produce lots of young?
Because it's a selected species, not king.
Yeah, it's because mammals do some sorts of maternal care in most cases, right? So they invest a lot in each individual young, right? And that goes behind that strategy, right? And that's why young mammals have a higher survivorship. Fish, they produce billions and billions of eggs very cheaply, spawn them out in the ocean, and then don't give a damn about them. Okay? So they have very high mortality at an early age. Very few of them survive. Okay? And so you can split mortality into kind of two components. So you have the total mortality, and then you have what we already know as natural mortality, disease, predation, and so on, old age, if you're lucky. And you have fishing mortality, which is the artificial mortality we impose because of fishing, right? And by simply looking at the number of fish in each age class and the trend of it, you can sometimes get an idea about what's going on. So for example, here, right, you have a transition point. So before age, 5, your mortality curve behaves like this. So your total mortality is 0.1 shape of the curve. Then you have a transition, it gets much steeper. That's because fishing kicks in at that age. So fisheries catch 5 years and older ones in this fishery, but not the young ones. So your mortality actually steepens because you introduced F, the fishing mortality. Okay? So this is very much theoretical. Rarely ever do you actually see this in real life, because usually real life is far more complicated. So there are various ways in which people try to estimate mortality. Right? However, it is very, very difficult. Okay? You can get a handle on fishing mortality far more easy. Okay? So you can do survival rate estimates, mark recapture methods, right? Which have usually very low sample size because it's very expensive to tag fish, let them go, and then try to catch them again. Right? But I think it's actually a really good method. You have other methods, age and length-based catch curves, and you have all sorts of complicated empirical derivations that I don't really want to get into at all. The main point I would like to make is that in stock assessment, natural mortality is very often not really estimated at all. Most stock assessments make an assumption about natural mortality. They just bluntly state M is 0.1 or something like that. Okay. There's a huge literature around that. Many stock assessment models says, oh, it doesn't really make any difference to the models are insensitive to it and so on. I could never really wrap my head around it mathematically of why they don't care about it. But as long as they do their model correctly, it seems to work. Okay. The main point is M is extremely difficult, almost impossible to really measure. Okay. It's hard enough to measure natural mortality for a population of small mammals in a field that you can actually observe and theoretically count every single animal, and you can watch them all the time. So it is almost impossible in the ocean where you rarely can see what is going on. So then we come to stock size. Right? So you can either estimate the absolute stock size, biomass on numbers using surveys, or use an index. And we already talked about catch per unit effort, which is an index. Okay, and there is a huge number of models and methods for estimating all of this. Okay, I don't want to talk about them because they're stock assessment models that I don't understand, and so I would just be making things up, all right, and scratch my head and just confuse you. But there is a huge number of them, and they get progressively more complicated as you go down the list. Okay, there's a huge literature on it. If you are quantitatively inclined and you're really curious to delve into that, there's a huge field to explore, right? And I've indicated some key resources. And if you're interested, talk to, when the lectures come, when Alex Hesp and maybe Ainsley Denham comes in from WA Fisheries, they're experts in this, right? And talk to them. Or volunteer to help them. That's the best way to learn. I want to make sure that I don't run out of time. So I'm going to skip that, stock recruitment, because it is also scratching my head. Let me just skip that. Instead, I want to talk about surplus production. We've talked about this before, okay? So I don't need to repeat it. Russell's axiom. Okay, so if there were no fishing, no catch, you can combine the growth and the recruitment into what the model calls production. Okay, remember agriculture? So the term is there. And so basically the next biomass is last year's biomass plus whatever the stock produces minus its natural mortality if there's no fishery. Very simple ecology, right? Applies to everything that's not hunted or killed. Okay. But it also implies that at carrying capacity, remember B0, your production equals to your natural mortality, right? Your stock produces as much as is killed because you flatlining your population, okay? Okay. And so the concept of surplus production is actually the amount of the population will increase, right, in the absence of fishing, or it's the amount of catch you can take. See if let me show it this way. You're already familiar with this, the logistic population growth curve, right? And you can re-express what's going on by plotting the fishing effort against your catch or yield. Okay. And so if we're up there at carrying capacity with no fishing, we're down here. There's no fishing, therefore there's no catch. Right? That's the easy point. And so as we then fish, remember we're lowering the population and we know that the population growth curve increases. We had this a couple of weeks ago, I think. Okay? So you're increasing your fishing effort and therefore your catch goes up. Obviously, right? It's logical. You keep going, catch increases, effort increases, population growth rate increases as well. You reach this point that we already talked about, okay? And so at this point, we have the maximum population growth rate. That means at that point of biomass, where we reduce the biomass to half of its carrying capacity, the population has the highest growth rate, okay? That means at that point, we get the maximum catch, because it produces the maximum amount of new biomass each year. Okay. And that translates to a certain amount of fishing effort at which we obtain that. And of course, if we keep going, we go beyond that. Okay. Which basically means, because the population growth rate is now decreasing again as the biomass goes down, if we put more fishing effort into it once this point, we're actually not catching more. That's why fisheries are not conveyor belt production factories. Okay. Because of this population dynamics. Okay, and so we end up over here, lots of fishing effort trying to fish like crazy, but the catch has been going down. Right? So current biomass is a lot less than the biomass at which we can catch MSY. Okay, so that's the core concept behind this, which means if you keep your biomass here in that zone, it should be kind of greenish, right? You can catch the maximum. So if your current biomass is at the level of biomass that produces MSY, you get MSY. But if your biomass, your current biomass is less than the biomass that produces MSY, okay, you're catching less and you're kind of in the warning zone, you're overfishing. And if your current biomass is larger than the biomass at which you catch MSY, you're on the safe side. Okay, right? As you see on the population level. Okay, so if you're over here, if your biomass you're here, which means you're over here in the catch curve, you're overfished the stock. And now you got to pay attention because these terms really matter. So you overfished. So if you have an overfished stock, you've reduced the current biomass to below the biomass level that produces the maximum sustainable catch. Okay. Now in terms of fishing mortality and fishing effort, the same thing applies, but it's a little bit the other way around. So we have fishing effort, therefore we have a certain amount of fishing effort called FMSY that produces your maximum sustainable catch. Okay, so we're no longer talking about the biomass, we're talking about the fishing effort. And so if the current fishing mortality is larger than the fishing mortality of MSY, your catches are going down. On the other hand, if you got the current fishing mortality that is less than the fishing mortality of MSY, yes, your catches are less, but you're on the safe side. Okay? So, if your fishing mortality is larger than the fishing mortality of MSY, you're overfishing. Okay? And if it's less, then you're not overfishing. So we have two terms, and that's the crux of the message that you need to have, right? Overfish, the term overfished relates to the biomass status. The term overfishing relates to the fishing mortality. And it's a key differentiation. And fishery scientists and managers use those two terms quite strictly. Okay? Overfished relates to biomass, overfishing to the fishing mortality as driven by the fishing effort. And they're different. So stock is overfished if its current biomass is below the biomass that produces MSY. But you're overfishing a stock if its current fishing mortality is above the fishing mortality that produces MSY. Okay? So it's really important to understand that difference. And that's, yeah, so that's the common convention. And the way you express that graphically is called Kobe plots, where you basically plot your biomass, usually as a ratio of current biomass to biomass MSY, so after stock assessment, and your FMSY ratio. So ideally, you want to be right here, because that's MSY. Produce the maximum catch, giving the fishing effort. But if you're over here, right, your biomass is above the biomass ratio of MSY, you're not overfished. And if you're below fishing mortality at 1, you're not overfishing. So that's the green zone. That's the happy zone. If you're over here, your biomass is below the MSY level and your fishing mortality is above the MSY level, you both overfish the stock and you're overfishing it. Okay? This is crucial that you understand that. Okay? And so here's the happy zone for biomass on the right. And there's the happy zone for fishing mortality. There's the overfish component on the left. And for fishing mortality, it's up or down. Okay? And so you can do that by species over time, right? Where you might find that a species starts off really quite nicely, and then as the fisheries develop, it gets into trouble, right? Overfish and overfishing. Management reacts, drops the fishing mortality rate back down, right? Stock starts recovering, and then fisheries kicks in again. Okay? And you see this sort of circular pattern over and over again for species. That makes the Kobe plot really quite useful for trends over time for given species. You can also use it to plot between species. So the current status right now, and see this, in this case they use spawning stock biomass, a slightly different concept, but the principle holds, right? And so you can have, look, these three species on the safe side. They're not overfished, they're not being they're not overfished, and there's no overfishing. But big eye is both overfished and overfishing is occurring. Okay. And I think I gotta, yeah, you can read all of that. But the main point is that you understand the Kobe plot. Right, I went over time. Let's have a little break and then we start the lab. Questions?